Okay, we're going to officially start here. Thank you, everyone, for finding time to come to the greatest Zoom experience you'll have for sure for some time. My name is Derek Pauls. I think many of you know I'm faculty at Berkeley. I'm joined here by the rest of Kevin's committee, Bjorn Hartman, Professor Simon Schleicher, and also Professor Nadia Peak from University of Washington, who have been outstanding in helping Kevin with his thesis work. Rundong Tian, who many of you know as Kevin, came to Berkeley. He was actually an undergrad and he was in mechanical engineering. He came here and I was really honored that he came and joined my group to work with me in 2014. It's been an absolute pleasure through so many projects, and it's always a mixed emotion because at the end they are the most productive, most energetic, most full of passion and creativity, and then you have to let them go. You're very, very sad, but you're excited because they will be doing great stuff in their next part of their career. Kevin is going to talk about a series of projects that he has done that focus on a broad landscape of really deeply looking at what I think future tools and the experiences we will have around them. And I'll let him kind of guide that. We're going to basically let him go. Hopefully there won't be any kind of major things to intervene. I'll try to answer anything on chat. At the conclusion of that, I'll ask for questions from the committee, and then we'll open it up to other people. Again, Kevin this is what a almost complete student looks like. This is number 8 for me, and so it's very exciting. He's a little special lucky number. With that, Kevin, please take it away.
Yeah, sounds good. Eric, thank you so much for that introduction. And yes, let us get started. Okay, hello everyone. Today I'll be primarily presenting on, like Eric talked about, these 3 main projects, each of which considers a different perspective for how physical hands-on fabrication can be mediated and augmented by computation. And by the title Lucid Fabrication, I'm roughly referencing the experience of lucid dreaming. And from that connection, I'm trying to succinctly capture this perspective, which in many ways is about reclaiming control over the process of fabrication. Before starting, I want to give a big thank you to all of my co-authors, Sarah, Jeremy, Ethan, Odant, Florian, Marika, and of course my advisor, Eric Paulus. I also wanted to thank UC Berkeley, the Jacobs Institute, as well as Siemens Corporation for the financial, institutional, and intellectual support that made all of this work possible. So starting with the high-level motivation, the promise of digital fabrication was that given these tools like 3D printers, laser cutters, or CNC routers, plus the imagination that you already had, anyone can make almost anything. These things can be useful, playful, but ultimately it's about being creatively engaged to make these personally meaningful artifacts. And of course, there's practical benefits to this approach as well. Using one of these machines like a laser cutter or CNC router, users can make complex geometries accurately and automatically. But of course, there's a catch. So in order to go from the idea of an object to fabricating that object, a maker must navigate a gauntlet of software packages to first draft a digital model, devise a toolpath for manufacturing, and drive the fabrication machine itself. So these software pipelines are super functional and mature, but they can generate an enormous amount of overhead and friction for communicating design intent to a fabrication tool. So if you're making 1,000 of the same thing, that overhead is perhaps less of a concern because it can be amortized over all of the copies. But the thing is, this workflow is approximately the same whether you're making 1,000 copies of an object or just one of those objects. So the challenges of using this workflow has motivated a lot of work in digital fabrication research. Some of the most well-known works in this area are interactive fabrication, which showed how users can directly and continuously interact with fabrication tools. So this was one of their prototypes where a user could use a transparent touchscreen at the machine itself to tell it where to go. There's also interactive construction, which allowed users to design and fabricate assemblies directly at a laser cutter. So users draw with different laser pointer tools to communicate the type of geometry they want to make at the machine. And also, there's been research in augmented hand tools that can correct the user's position with respect to a predefined model. So that's been explored both for planar materials with visual fiducials for position tracking, as well as 3D sculptural objects with magnetic sensing and position tracking. And you may be more familiar with the autocorrecting router as Shaper Tools, which is the company that emerged from that research project. Taken in context of the overall history of digital fabrication, however, these works are relatively recent. So from the 1950s, people were already developing how sensors and actuators could control the motion of a tool. And here, this image is from the automatically programmed tool, or the apt system, which is describing how a user can write a program in the APT language, which then can be compiled into the punch card tape that could automatically control the tool. So at this point, numeric control was already figured out. So how do you get a punch card to drive a machine? But here, now they're starting to think about what's kind of the precursor to computer-aided manufacturing. So how can those toolpaths be automatically generated or compiled? So with this longer history of digital fabrication in mind, I wanted to call out two pieces of really relevant early work that aren't mentioned very often in the human-computer interaction community. The first example is conversational machining. So with this style of control, an interface at the fabrication machine allows the machinist to set up the tool for common operations such as drilling a hole pattern or machining out a pocket. And in this screenshot, the interface is used to create a toolpath for milling a circle. And you can see how it has these fields for, oh, where do you want the center? How big of a radius? How big of a tool are you using, etc. And this was something that was invented by Herco in the late 70s. And nowadays, most machine tool manufacturers have some style of this control. And if we look back at the original patent, this technique was, funnily enough, referred to as interactive machining. And as we can see from the description, the inventors of the system were also thinking about how part programming, or the process for defining what and how the machine should fabricate, could be done by the operator at the machine location. The second piece of related work that I wanted to share is something called record playback, which was developed roughly around the same time as numeric control. So this was even earlier in the 1950s. And to me, this is one of the most interesting pieces of related work. So record playback did just that. The system recorded a machinist's actions as they're cutting as a means of generating the toolpaths that can be played back automatically. And because it's a manual tool, the way that you generate the toolpath is more direct, more flexible, and it leverages the existing embodied knowledge of the machinists. And not to mention, you get a part immediately after quote unquote programming the toolpath. So I think you'll note that there's some pretty fundamental differences between how numeric control, writing punch cards, and record playback approach the question of how to incorporate computation into fabrication tools. So commenting on those differences, James Fallows in his review of Forces of Production writes, with numeric control, machinist skills were devalued and viewed as little more than a series of straightforward operations. But record playback programming was, as one proponent described it, programming by doing. The program, therefore, was a record not only of the machine and stylus motions, but also of the machinist's intelligence, skill, tacit knowledge, and judgment, which were embodied in those motions. Rather than viewing the possibility of human intervention cynically as merely the chance for human error, this approach viewed it positively as the opportunity for human judgment, skill, and creativity. So though these projects are not as well known, these early works occupy a lot of the same conceptual territory as these more recent projects. For example, how can a user work with a digital fabrication tool more directly? Or alternatively, how can we leverage the familiarity of hands-on control? And in hindsight, these similarities aren't too surprising. They're all trying to grapple with that same fundamental question around how can or how should users interact with the computation that's being incorporated into these tools. So moving from related work to my own work, I'm similarly interested in reducing the viscosity of conventional digital fabrication workflows. And to do so, my exploration in this space is guided by this high-level research question. How can digital fabrication tools engage opportunities for human judgment, skill, and creativity during the fabrication process itself? And this question is very much inspired by those earlier hands-on approaches that we talked about. So this work is not about more intuitive computer-aided design or computer-aided manufacturing tools, nor is it about less opaque machine interfaces, though those are important questions. But rather, it's about how the fabrication tools themselves can be designed to support the fact that hands-on making is this really interesting site of creative exploration and problem solving. And methodologically, I build interactive systems to explore these ideas. And in this talk, I'll share 3 complementary approaches that allow makers to bypass these conventional workflows while still maintaining many of the benefits of digital fabrication. Okay, I'll briefly check the chat before going to MatchSticks. So the first project that I wanted to talk about is MatchSticks, a fabrication system that was designed specifically for woodworking joinery. And the main question that guided this work was, how can design intent be more directly communicated to a CNC tool for woodworking? So compared to how we would use other tools in a wood shop, like say a drill press or a table saw, CNC machines and their associated workflows feel uniquely out of place. We were interested in capturing some element of how we can work directly and fluidly with these manual tools, but that doesn't necessarily mean that the tool has to be necessarily operated by hand. And the main focus, and this project focuses on one aspect of woodworking in particular, which is joinery. So many larger wooden objects and structures are made by assembling separate pieces of wood. And as a result, one crucial element to figure out is how exactly will those separate pieces of wood interface with each other. With those goals in mind, we created MatchSticks. First of all, this work is very much in the spirit of interactive machining. So users can select a joint to fabricate directly at the machine. 2, not only are the interactions focused on joinery, the mechanical layout of the tool itself has also been tailored for the specific constraints of machining joinery. And because we're focusing the capabilities of this tool on local geometries rather than trying to mill out the entire object, it can make objects much larger than the machine itself. And next, I'll go through one workflow for making a box while highlighting some additional details of the system. So in this workflow, we'll start with the design. And we'll notice that we're not in front of a computer because we've abstracted away a lot of the hard parts, such as the joinery. The remaining elements of the design, such as the topology or the dimensions, are fairly easy to keep track of in your head or with some simple sketches. Next, our tool is positioned within the ecology of existing woodworking tools. The goal isn't necessarily to replace any one of them, but to aid in one of the most difficult aspects of furniture construction, which is the joinery. An example here is that for a simple cut like this, a table saw is used. There's no need for the complexities of a CNC machine for this simple operation. And to cut a joint at the machine, the user first selects a joint through the onboard touchscreen. And then once that joint has been selected, the user can mount the material to the machine and start the milling process. So from this angle, we can see the arrangement of the gantry more clearly. Normally a CNC tool for woodworking conjures an image of, say, like a flat pack router perpendicular to a really large work surface. But here we have something that's a lot more focused and a lot more geometry conscious. And finally, because these components can be iteratively created and assembled, the workflow isn't one of get everything as perfect as possible and then hit the play button ideally once, but we can think about how we can interact with this machine incrementally and improvisationally. Oops, forgot to put the video. One aspect of the system that I wanted to highlight is the fixturing. So there's a really broad range of woodworking joinery, many of which require the wood to be oriented in a particular way with respect to the cutting tool. For example, sometimes you might want to machine on the face of a piece of wood, and this is the orientation that conventional CNC routers like to do. But other times you might want to machine the end grain or the edge of a wood, as well as in these other configurations. So for example, cutting a contour along an edge, cutting pieces at an angle, or maybe cutting round stock. And as a result of the way that we've designed the layout of the gantry as well as the fixturing, MatchSticks can machine a wide variety of joints, which gives users a lot of flexibility in terms of the topology, like how the pieces of wood are meeting together, as well as in terms of aesthetics and strength. So here we can see how these different types of joints are used in context of a piece of furniture. And again, because we're using the precision of a CNC machine locally and discretely, we can create objects that are much larger than any dimension of the machine. Another example that I wanted to show is this toolbox. So to create really precise joinery, the wooden components are typically squared and flattened with these large machines to establish reference surfaces before any of the joints are cut. But here, these pieces weren't fed to those machines, which are called planers and joiners. So instead, when we cut the joint, we can machine not just the joint, but all the surfaces where the joint meets to establish those reference surfaces locally. To probe reactions to our approach, we conducted a small user study to elicit qualitative feedback about our design. So users were invited to fabricate a simple frame using a more structured tutorial workflow, as opposed to the more open-ended one described previously. So in the tutorial workflow, the interface on the machine also guided them. The interface on the machine guided them through making this box, reminding them to keep track of things like reference surfaces, as well as offered in-context fabrication guidance for things like fixturing. And overall, participants responded positively to our tool, commenting on the flexibility of this alternate workflow, as well as how it challenged their perceptions of joinery as prohibitively difficult or intimidating. So in particular, participants with more limited exposure to CNC felt empowered by the tool. One of our users with no prior experience with CNC machines said that, "I feel like I can do so many more things, like it gives me so many more options. I thought that CNC is for when you're older and know more things and understand all the coding and stuff." This is eye-opening because I realized that CNC machines can help me even if I don't understand all of that. So the complexity of existing CAD/CAM workflows, computer-aided design, and computer-aided manufacturing workflows, is both a real and perceived barrier to entry for beginners who want to engage with these machines. And here, the perceived barrier comes from this assumption that working with a CNC tool is somehow this more sophisticated or more fancy way of making. Participants also commented on how MatchSticks differed from existing tools. So speaking about existing workflows, one of our users who is familiar with both hand tools and CNC tools summed it up succinctly. With digital fabrication tools, you have to have it perfect before you hit the play button. Then comparing our machine with hand tools, the same user goes on to say, when you're doing something with scrap materials, you end up changing things here and there as you move through it. So hand tools and maybe MatchSticks a little bit as well, you're working with what you have as you move along. It really is an in-between. It's quick like a hand tool and it's empowering like the CNC. And enabling this type of workflow that can be improvisational and serendipitous was really one of our main goals. CNC machines are no doubt super powerful, but there's definitely ways of engaging with their capabilities outside of established workflows. But of course, there's limitations to this approach. While many users felt empowered by the tool, there was also a sense of detachment that came along with having the machine do most of the making. For example, for P1, who had a little bit of prior experience with CNC tools, they said, the design is in my control, but the process is not, which is good or bad, depending on who can do the process better. In this case, it's definitely the machine. I do feel a little out of control of the fabrication process. So I think this picture kind of succinctly summarizes that feeling, as well as some of the opportunities that I was interested in exploring for the next project. So first of all, MatchSticks was really focused on allowing users to directly articulate design intent. But after a user has specified a geometry, they just kind of sit back and watch, much like a standard CNC tool. Fabrication machines aren't these omnipotent tools that can make anything you tell them to do, but they can also be a rich source of feedback about the fabrication process. So instead of thinking only about how to allow users to directly articulate design intent, how might users more directly perceive the capabilities and constraints of the fabrication system? So in other words, how can we think about how can we go from thinking only about control to also thinking about feedback? In addition, we achieved directness in MatchSticks with a set library of geometries, but how might we support users in the creation of open-ended geometries? So we were interested in those ideas broadly, but to begin to explore and implement them in detail, we chose one fabrication tool as a case study, which is a lathe. So lathes are especially good for creating cylindrical geometries, like these objects that we made using our system. And the way that a lathe works is that here, the black cylinder, which is the stock material being cut, is held by the lathe, which rotates it about its axis. The triangular object, the cutting tool, translates on a 2-axis gantry to shape the stock material to the desired shape. And here I'm using one of these dials or hand wheels to control each axis of the gantry. So when I turn that hand wheel counterclockwise, the tool moves right to left. Like I mentioned, one of the main ideas that motivated this work was feedback. And specifically, how can haptics mediate the experience of directly interacting with a digital fabrication tool? And one thing I want to emphasize is that the important thing with haptics is that we're not limited to recreating what using a manual lathe feels like, and nor should that necessarily be the goal. So the main idea behind our system is to keep the manual control, but then have the coupling done by wire. So instead of a physical coupling, like something like a mechanical transmission, we can create a programmable coupling through software. And that coupling is bidirectional. So the hand wheels that the user is interacting with are actually haptic controllers. So using those controllers, the user can control the lathe, but they can also feel different types of force feedback. And because these hand wheels are like a pretty specific interaction modality, we complement that with a general purpose graphical user interface for things such as tool selection or modifying settings. So we leveraged this turn-by-wire architecture towards 3 primary themes. The first is intent. So how can design intent be expressed more concisely? How can we capture the most salient aspects of what the user is trying to make? The second theme is complementary, the inverse of the first, which is about perceiving state. How can users understand how the work is progressing? As I've mentioned before, fabrication tools aren't just these static objects that we can impose design will upon, but they can and should also inform us about their capabilities and constraints. Lastly, we have scaffolding, which is a more specific type of feedback. How can the tool inform the user about technique? In other words, how can the tool teach the user how to use it? So the first interaction that I wanted to show you all was snap to guide. So in our system, users can set virtual haptic guides through the graphical user interface. And then with the hand wheels, they'll physically snap into these guides when the tool approaches the predefined dimension. And here we intended this as a lightweight way of capturing something that we only associate with digital fabrication tools, which is automatic accuracy. Next, if you want to cut something like a radius on our system, you can use a virtual tool. So when the virtual tool is activated, a single hand wheel can move the tool along an arbitrary path rather than its designated axis. So instead of using a special jig or coordinate multiple inputs simultaneously, or grind your own lathe tools, if that's something you're interested in, we can remap the coupling between the hand wheel and the lathe in software to expose the controls that most succinctly capture the most important aspects of the design. And we've also revisited record playback. And here we've implemented an interaction similar in style to some end user automation tools, for example, actions in Adobe Illustrator. So after the action has been recorded, the toolpath can be reviewed and played back. This way, if you need another copy or made a part in a way that you really like, you don't have to repeat yourself. The second theme is state. So state can be communicated continuously through haptics. While cutting, users not only control the position, but they feel a simulated reaction force proportional to the amount of material that's being removed. And the reasoning for this is that the first indication that something might be going wrong shouldn't be that the tool breaks or the part is ruined, but that you should be able to feel that change immediately. And because the coupling is done through software, it's not fixed. So if you're using a super delicate cutting tool, you can crank up the gain of the force feedback. Lastly, how can the system teach the user how to use it? There's a really wide range of lathe tools and varied techniques about how to use them. And in this example, the system is enforcing best practices for drilling. So rather than to cut to final depth in one go, it's often better to peck at it incrementally to get the chips to clear out. And here, the hand wheel is physically resisting the user's input to show that the cut material should be cleared out first. And this is just one technique that our system supports. So far, we've talked about turn-by-wire as very much this black box. So here, I'll briefly discuss the architecture. The main takeaway is that we have microcontrollers that interface directly with the hardware, like the lathe and the hand wheels. And this gives us the timing regularity of real-time control loops for things such as the haptic feedback. But at the same time, we expose interfaces that can be coordinated by high-level programming languages, by high-level programming languages to develop the interactions in. And the latency to go from the web browser, which is doing most of the heavy lifting, down to one of the hand wheels and back again is on the order of 10 to 20 milliseconds. In terms of the hand wheels themselves, the mechanical design references the configuration found on traditional lathes. And for the haptic controllers, a motor with an encoder is acting as both the sensor and actuator. For the haptic rendering itself, we're using a combination of electronic braking for passive force rendering, as well as impedance controller for the active feedback. So for things such as the snap-to-grid. To probe reactions to our system, we recruited 5 expert fabricators to create the simple component using turn-by-wire. So the participants were recruited from the staff of an educational makerspace. The component was designed to expose users to all of our haptic interactions. And all 5 participants successfully created this widget within 15 to 20 minutes after a 15-minute training period. And next, I'll briefly share some of the highlights from the semi-structured interviews that we conducted after they used our system. So one of the interactions that the participants liked the most was snap-to-grid. And here P5 said, the ability to set the limits so you don't cut too far and actually helps you make the exact dimensions you want. That sets it apart from any other machine. Just manual machine or digital readout, a DRO, doesn't physically stop you from going past those limits. Many of the participants were also surprised by how easy it was to learn. So P1 said, it was a lot more comfortable than I expected because in the beginning you told me it's kind of a CNC and I thought the learning curve is going to be bigger than what just happened today. And this was a sentiment that was echoed by many of the other participants. So even for some expert users who are really familiar with CNC machines, they don't necessarily think of learning a new CNC controller as a straightforward task. Lastly, is turn-by-wire a manual tool or is it a CNC tool? This question prompted a range of responses from our participants. 2 participants thought that it was closer to a manual tool because of the hands-on interactions required. 1 participant thought that it was more of a CNC tool, noting that under the hood, the system is in fact a CNC lathe. The remaining participants were somewhere in the middle. And P4 on this topic said, I feel like it's right down the middle. If I'm trying to do a hand plane and it's not cutting, it's either the way that I've set it up or my technique. But here there's that kind of black box with a question mark on it between me and the operation of a lathe. And I completely agree with this sentiment. The by-wire architecture enabled these new interactions that we chatted about, but to do so, the trade-off was that we have to introduce some ambiguity compared to how a true manual tool is used. So to summarize, the architecture of turn-by-wire enabled interactions such as record playback, which we can think of as copy and paste, snap to guide, virtual tools, and in-context tutorials. So I think these interactions sound slightly familiar because another way to think about them is that these are actually the capabilities we associate with digital editing, but now applied directly to a physical editing task. And I want to emphasize 2 things. So if we extend this idea forward, there's many other digital editing capabilities that can be explored. For example, things such as undo, redo, maybe autocomplete, or editing the recordings, either manually or automatically. But the other thing is, instead of by-wire control for a single tool, how might we digitally mediate the control of any tool? So imagine having something like snap to grid, but now for any one of these fabrication tasks on the left. A piecewise approach is possible. So for each tool that we're interested in augmenting, we can develop a system around that tool. However, an alternate approach that's perhaps more extensible is to augment the user and the fabrication environment directly. And that idea is the motivating concept behind the most recent work, aDroid. So rather than augment each tool individually, we can use a robot arm to mediate how the user controls any tool. And more specifically, how can the interactions that emerged from turn-by-wire be extended? So how can the capabilities of digital editing be broadly incorporated into hands-on fabrication? So the approach is inspired by physical jigs and fixtures, which support users by selectively constraining the many degrees of freedom in our bodies. For example, a miter saw constrains the handsaw to move accurately within a plane, and a drill press, or in this case a drill jig, constrains the motions of a drill to move only along a line. So to help us reduce the number of degrees of freedom in our bodies, a variety of context-specific jigs can be used, depending on which degrees of freedom you want to constrain. So the main idea is that with aDroid, the robot can render fixtures virtually. So robots are typically useful because we can tell them what to do, but here we invert that. It might be equally interesting and potentially easier to tell them what not to do. So here, the toolpath is not predefined. So as I'm trying to move the tool, motions are generated on the fly as the system responds to my applied forces and the current constraint. And the compliance of the robot can be tailored to the task at hand. For example, when we want to drill, as opposed to just moving the drill around, we can get the robot to constrain all of the motions to be along the axis of the drill bit. And here we're seeing one of the other features, which is snap to grid. So in terms of the lines that we're seeing, those haptic interactions are complemented by a projection augmented reality interface, which in this case is offering in situ visual feedback about the tool's position. So before describing the interactions in more detail, I just wanted to recap the main parts of our system. So first, we have the robot itself. We have a projected augmented reality display. So there's a video projector to the right of me outside of the frame of the photo. There's a custom force torque sensor that senses the interaction forces between the user and the robot. And lastly, we have the tool, which is outfitted with a bracket for attaching it to the robot, as well as buttons for user input. To demonstrate a range of interactions, I'll show 4 tools that we prototyped with aDroid. And each of these tools will highlight a specific part of the system. For example, with the measurement probe, I'll show how the initial correspondence between the physical and digital models can be established. With the track saw, I'll show how the system can record a user's fabrication process. With the drill, I'll demonstrate how accuracy can be borrowed from an industrial robot during manual fabrication. And lastly, with the camera rig, I'll show how users can define custom constraints to tailor the system for their tasks. So the first one that I want to start with is a drill. So to use a hand drill with our system, the user selects that option through the graphical user interface and mounts the tool to the robot. After the drill is loaded, the AR system projects crosshairs onto the table to show where the drill is pointing. When the drill nears one of the virtual grids, it will physically snap to the grid, like a haptic controller. When adjusting the orientation of the drill, the AR view visualizes the current heading and elevation. And for precise drilling, the user can press the latching button to constrain the drill along the current axis of the drill bit. And here, the user is working with that measurement probe. So the probe tool can be used to directly measure the location of objects. When the tip of the probe contacts an object, the robot automatically retracts the probe to the safe position. So the probe tool can be used to locate specific types of geometries, in this case, the edge of a workpiece. For the track saw, the robot guides the intermediate tool, the track. So the stock material is mounted to the workbench using double-sided tape. And the AR view is projecting where the cut will occur relative to the track. Before cutting, the user presses the lock button on the ruler. And then the cut can occur when the ruler is locked onto the surface of the workpiece. After a cut has been made, the AR view displays the distance between the last cut and the current position. And the user can also navigate the history of previous cuts, like a lightweight CAD model. Lastly, camera rigs, such as cranes or sliders, can also be thought of as jigs and fixtures, mechanisms which selectively constrain the motion of a tool. So to define a virtual slider, the user first moves the camera to a desired start position and sets that position using a graphical user interface. The projection augmented reality view displays the X and Y position of that start location, as well as the current location of the camera. After setting the end position in the same way, the rig is ready for use. All of the user's motions are now constrained to go along that virtual slider. So I want to emphasize that the specific interactions we demonstrated can definitely be mixed and matched. For example, the ruler tool can be equipped with snap to guide, or the drill tool can be programmed to remember all of the previous holes that have been made. But for the sake of breadth, we chose just to demonstrate one aspect of the system with each tool. And here I'll briefly talk about how the system was designed and implemented. In terms of the high-level description of the software architecture, there's one main server which choreographs the interactions. All of the UI elements, including the projection AR view, are rendered in the browser. The main server, as expected, is also communicating to the KUKA's control cabinet, as well as the custom electronics on the wrist. So similar to turn-by-wire, the code for interactive control is sitting on my laptop rather than inside the KUKA's control cabinet. And the main motivation is similar as well. We want to offload the code away. We want to offload the code for these interactions away from the low-level KUKA programming language. Another important part of the system is the force torque sensor, which is central to all of the interactions I've described. So these sensors can cost upwards of $5,000. So not only are the costs of the robots themselves prohibitive, so are all of their accessories. So I was able to make one for under $100 with standard makerspace tools, which achieves similar resolution as commercial sensors. So I developed the sensor only as far as to support the interactions described in this project, and there's definitely room for additional refinement or characterization. However, we're hoping that the sensor architecture can act as a viable starting point for other researchers who want to explore haptics or just force-based interactions in general. So on the right, we can see how it's mounted between the robot and the desired tool. And on the left, we can see the mechanism, which is basically just a really stiff spring. So if we measure how much it's been displaced, which is usually just on the order of a few microns, we can infer the forces that have been applied. So, and I'd be happy to chat more about the two details during the Q&A. So unfortunately, we weren't able to have any in-person user studies due to COVID-19, but we did conduct 1-hour interviews with a small group of experienced fabricators across 4 different domains. The interviewees we recruited were a mechanical engineer who has worked on underwater and aerospace vehicles, a director of fabrication services at a campus makerspace, a luthier or someone who makes stringed instruments such as violins and cellos, as well as the owner of a contract manufacturing shop. So on average, these interviewees had 17 years of fabrication experience across both manual and CNC tools. During our meetings, we showed them the videos of the interactions, and we conducted a semi-structured interview to elicit high-level feedback about the design. So the concept of having virtual jigs and fixtures quickly resonated with the luthier and fabrication shop director, both of whom have significant woodworking experience. So on this topic, the luthier said, usually in the workshop, most of the time that you spend is just setting up the machinery. So when you set it up, you want to make sure that you're making as many parts at the same time so you're not wasting the setup time. And so having something that you don't have to set up, it's buttons on a computer instead of a physical screw that you have to turn, that would make everything a lot more fluid. The fabrication services director interacts with a lot of students regularly. And one thing that they were most excited about this work was how it could make power tools more accessible in terms of confidence and safety. So this allows anybody, shape, size, age, whatever the ability to do these things on their own. For me, that's the most attractive sell, regardless of precision, quality control, and all that stuff. For me, it's a matter of empowering users. So in particular, P2 was thinking about the physical weight of the drills, as well as the kickback that they can potentially generate if you were to hit a knot in a piece of wood or a nail or something like that. In addition, the participants proposed a wide range of scenarios for applying this concept forward. For example, with painting or carving with a router, as well as secondary operations, so like reaming, tapping, or installing threaded inserts. They were also excited by the idea to use the projection system to visualize how to lay out a design, as well as using it for kind of redundant tasks like sharpening tools. To summarize, I wanted to emphasize on the benefits of having a virtual, quote unquote, virtual drill press. First, settings for the drill press, like the drilling angle, can be rapidly and accurately set or restored. Next, not only can it constrain the motion of the tool, it can also mediate forces to generate sensations like snap to grid in the real world. Also, similar to turn-by-wire, because all the interactions are mediated through software, the drill press knows where and how holes have been created. So when the user is directly fabricating with the tool, they're generating the same kind of data that would be generated through computer-aided design and computer-aided manufacturing workflows. And lastly, the drill press can be reconfigured to become other jigs through software. So where do we go from here? With the three projects, we saw how conceptually they pivoted off of one another. For example, whereas MatchSticks was focused about user control, we then considered the opposite with turn-by-wire, machine feedback. And next, both turn-by-wire and aDroid were thinking about digital editing capabilities for hands-on fabrication. But whereas one realized this idea in a single tool, the other thought about it in terms of an extensible system. And I think there's many exciting ways to explore this space, and I'll present two of those potential pivots. So the first is to take MatchSticks away from this turn-taking conversational style control to continuous control. And of course, we can experiment with things like hand wheels, like turn-by-wire, or direct hands-on control, like aDroid. But it would also be interesting to explore different ways in which continuous control can be abstracted. So what I mean by that is, what if you could machine with MatchSticks using like a 3D mouse, or a game controller, or even that same touchscreen tablet? So because the control is done by wire, there's no physical limitation in terms of the form factor of the controller itself. And with any one of these controllers, we can have similar support from features like Snap to Grid or virtual tools so that we can still create accurate complex geometries. The second is to kind of go from this super maximal environmental level intervention that we saw with aDroid and start thinking about how computation could instead be incorporated in much more minimal ways. So for example, how could a regular track-saw track be minimally augmented with computation? So here, the blue triangle that's at the top right of the screen is just used to keep the track square with respect to the bottom edge of that wood. But maybe that blue triangle could actuate the track side to side to quickly index through a cut list. Or maybe something like a circle guide, which works like a giant compass. But instead, maybe the radius could be actuated. So you could cut a circle just as easily as an ellipse, or just as easily as like cutting a square. So here I wanted to back up a little bit to the high level motivation behind the work. So in the same way that 3D printing software slicers have a draft setting versus a high quality setting to suit different situations and constraints, or that a makerspace might have many different types of 3D printers that span different fidelities, materials, or requirements, the interactions and workflows for digital fabrication tools can be similarly diverse. So the workflow for making many different objects with a fabrication tool doesn't have to be the same one as the workflow for making many of the same object. And the tool interface for skilled machinists steeped in tacit knowledge doesn't have to be the same as the one for someone who's more familiar with computer-aided workflows. In this talk, I demonstrated three alternative ways for engaging with digital fabrication tools, which looked at how interactions that look like hands-on making can achieve many of the advantages of digital fabrication, or have the characteristics of digital editing. With MatchSticks, the contribution was a new style fabrication machine designed specifically for one of the most important building blocks of furniture, joinery. And the way that you interact with these capabilities, it's in a way that's more like a manual tool, like a miter saw that cuts joinery, rather than a CNC tool. And this draws inspiration from conversational machining, and we've applied it to a domain that's really well suited for parametrized library of geometries, joinery. And with turn-by-wire, the novelty is definitely not the tool itself. Lathes are one of the oldest tools invented by humans. But how we interact with that lathe is unique. So during fabrication, the force feedback communicated by the lathe conveys additional layers of information that go beyond the literal or real forces that are felt. And separately, but overlapping with haptics, we've created a physical fabrication system that supports editing capabilities we typically associate with digital editing. And lastly, with aDroid, I showed how a robot can support the process of hands-on fabrication with virtual fixtures and jigs. But not only that, these virtual fixtures allowed us to inject capabilities of digital editing that we saw with turn-by-wire, like Snap to Grid, within hands-on making more generally. So collectively, I just want to emphasize that these techniques are not meant to replace any existing interactions or workflows. Much in the same way that a high-end 3D printer for superfine surface finish doesn't replace the desktop printer for on-demand iteration. Instead, there's a lot of opportunities to think about how not only can the capabilities of digital fabrication tools be flexible and adaptable, but so should the ways in which we interact and engage with those capabilities. And in particular, one of the most powerful things that can be leveraged are these embodied interactions that allow us to exercise judgment, skill, and creativity during the fabrication process. And with that, thank you all for your time, and I'd love to answer any questions.